At least the first three books. Love to pitch those ones. And jumping out of the airplanes. I like to skydive, so. Okay, that's enough about me. Quick disclaimer, this is my presentation. I got sent here by my company Nightwing, but this is my presentation, not their views. So anything I say here, it's not theirs. Okay, so for this talk, I'm assuming that you guys are pretty new. I'm pitching towards that. So if you're a LLM expert, if you're a language model expert, if you do machine learning on the outside, this is probably going to be like stuff you already know. But I'm taking this from a very security-focused standpoint. This is for any red teamers that are new to LLMs, security noobs, blue teamers who are new to LLMs, or really just anyone new to LLMs. Okay, so before we get started, there's some things that we need to make sure we're on the same page for. Specifically, some definitions here. So I want to make sure that we go over and let you understand what an LLM is, which may seem kind of basic, what a backdoor is, what a trigger is, and then just what jailbreaking is. So first, let's take a look at what an LLM is. I'm going to break this down into 4 different levels, kind of trying to take the explain like I'm 5 approach here. At the very lowest level, it's literally just ChatGPT. It's a robot that can answer questions and give you some feedback. So that's what you would tell a kindergartner. That's what you should start out knowing it for. For someone who's in high school, I'd say it's a tool that lets you do some really cool research. It can search massive data sets in really cool ways, and it can search both audio, images, as well as actual text, and effectively any sort of content that you can figure out how to represent as a vector. And if you're in college, we can take this a little bit further. We can say that it's a special kind of database that holds a bunch of numeric values that represent the semantic values of a word or of some item, basically, and how they relate to a whole bunch of other things in the same sort of space. And it's been created by processing and analyzing a massive amount of source data. That's very important. It has to come from somewhere. You can't really just create this out of nothing. You have to have something to work off of. It's supposed to basically map some massive data set. And once you have that, you're able to query that in some sort of natural language method. So you can talk to it like you would talk to anyone else and say, hey, I am looking for a thing, rather than saying search for, or like select star in all of blank. Right? So it's not like SQL, it's a much more natural interaction. A small part of that, though, is that the way that you actually talk to it is dependent on what it was trained on. So if you trained your language model on exclusively Spanish, and then you tried to ask it an English question, it's not going to know how to respond. It's going to try. But what it's going to do is it's going to take that question and it's going to break it up into tokens, and then send those tokens to try and get some stuff back. And so it's going to give you back some weird output that you don't understand. And that even if someone like who knows Spanish was reading it, is going to look at it and be like, this is weird. I don't know how it got here. So interesting little artifact there. And then finally, the more advanced one for someone who's in grad school, at least beyond their undergraduate studies and has a kind of an understanding here. It's a vector database that contains a massive set of tensor values. Tensor values are massive arrays of numbers. And they are either integers or they can be decimals. It's kind of up to what they want. But they're supposed to allow you to describe hyperdimensional artifacts or values that can be used for really interesting purposes. And this is, again, created by training on a massive data set. When you've trained it, you're able to use it to describe the semantics of that input data set. And it can be queried using a similar linguistic pattern to the source data. Like I was just saying, if you put it in Spanish, you need to use Spanish to query it. If you put in English or whatever else, images, doesn't matter. Whatever you put in, that's how you need to query it from. Okay, now moving on. What is a backdoor? Backdoor is something that exists in the model that is malicious and was put there intentionally. That's not something that was accidental. If it's there accidentally, that's a bug. Backdoors are basically a superset of bugs. Every backdoor is a bug. Not all bugs are backdoors. It exists in modified embeddings in the model and that will affect the output of the model when triggered by a user query. So what that basically means is that someone did something to the model, the data or the embedding model, whatever. They put something in there so that when you interact with it, it will do something that the people who created the model did not intend. So it's just the model acting outside of what you would expect. Okay, and what is a trigger? A trigger is just the way that you will literally trigger that backdoor. That comes in as a number of different formats. A trigger is some type of input that results in a backdoor within a model being activated. Triggers can be effectively infinite number of patterns, so it doesn't have to be something that you would understand. It could be something as simple as like execute order 66, but it also could be flag or not blah, blah. Like, it does not matter. You can put in all sorts of stuff here. And then jailbreaking. This is mostly for clarification. Jailbreaking has a presence in a lot of different areas, including for anyone who's done like iPhone jailbreaking back in the day. At this point, it's a lot harder for anyone who has tried it. Jailbreaking effectively does not exist. It does still technically exist, but that's getting off topic. It is a broad term for any sort of attack on a model with the intent of getting it to misbehave. Okay, so next, let's go over some context. We need to know how a model that is ready and in production, how it's been deployed, what that looks like. So I'm going to go ahead and show you guys what an example pattern looks like. And just for clarification, the pattern is different from the actual architecture. Pattern just means how do you get it deployed, not what does it look like once it's deployed, but how do you get it to that point. And it's just going to be hello world level, so don't worry too much on that. And then I'm also going to go over the example architecture, what it looks like once it's deployed. This is that. That's pretty simple. You can say on the left side, you need to start with some sort of foundation model. Unless you are someone like Google, one of the major ones who's actually creating a foundation model, you start with something. And what you're going to do is you take that and you do some sort of fine tuning on it. So you will take that, that model and add in whatever your domain is. So if you are using it for trying to find, what's a good example here? You're using it to try and look through your own internal documents. You have, let's say, an enterprise that has 100,000 documents, and you need to be able to like ask the model about those documents. You take those documents and you train your foundation model on that in order to end up with your model that you can use in order to query it. Once you've tested it, you say, hey, is there room for improvement? Is this doing what I wanted it to? If so, then you go ahead and find, or then you go ahead and send it to production. Otherwise, you go ahead and fine tune it, get it to the point where you want it to, and then you send it to production. And then that CM on the side stands for continuous monitoring. What that means is that when models are deployed, they're continuously being looked at for their performance and whether or not they are drifting at all. There's some things called a model drift or bias drift, which you can test for when they're deployed to see whether or not your model is starting to exhibit basically false answers. Like if it's been updated over time or people are starting to ask different questions and it's now giving different answers and it's starting to give things that were not looked for and it's time to do an update to the model at some level. The slightly more advanced version, and this is just for someone who's actually doing this in production, you're going to go ahead and add in the prompt engineering once you have your foundation model picked out. And then you're also going to assume you have some sort of team that is specifically dealing with some sort of special labeled data. Not supposed to be there. Okay, so the deployment architecture looks like this. So you start out with some sort of UI. That is the thing at the very front. That's the thing that whoever is going to be using your LLM is going to interact with. At that level, they're going to make the query. That query gets sent to an embedding model. And that embedding model is the thing known as like a tokenizer or the transformer. It takes that query, it breaks it up into something called tokens. The tokens are the actual vectors that it's going to use to search in the vector database. It's going to send that vector stream, the token stream, to the vector database, and it's just going to say, hey, give me things that are similar to this. And it will send you back stuff. From there, what it's supposed to do is it takes the context, whatever it's found at this point, and it sends it to a filter. This is how it should be set up. That filter is what you might know as like guardrails or like safety policies of some sort. That's them trying to make sure that whatever gets pulled back from the vector database is not PII, or health information, or whatever else. Maybe it's private information or something, or whoever is trying to ask this isn't allowed to have it. Doesn't matter. There's some things you want to scrub out. Once it's done that, once that's happened, it sends it to this thing called a prompt optimizer. The prompt optimizer is basically taking the initial query that someone had, as well as the filtered results, and it's going to go ahead and create a merged prompt, basically, which then actually gets sent to the actual LLM API. At this point, it's got two ways that it's going to go. It's going to take that context that it has, that query, and it's going to store it in cache. So if John asks about what happened to document A, or like what is the purpose of division B or something like that, and then Jane comes by later and asks the same question, instead of going through the entire process of trying to look up everything, create that embedding model, go through and do the whole thing, it's actually going to go to cache. It's going to say, hey, all right, I already have that answer, let's send it to them. And that will, as we'll talk about a little bit later, actually be one attack vector. After it's done that though, it also goes ahead and has a secondary filter. This is the point where it's, before it's actually sending things out, it's verifying that what it's sending out is okay to send out, or it's supposed to be doing that. And then it sends that back to the user. Okay, so at this point we've kind of got the basics. Anyone sort of confused at this point? Cool, everyone's nodding along. Let's go ahead and talk some attacks. So at a high level, attack vectors coming up, basically two flavors. There's poisoning-based attacks, which are when you attack the model at when it's being constructed. So before it's actually been deployed, you're trying to get in and mess with the way it's being constructed. And that's by targeting some source data set. That source data set is very possible a public data set. Because of the size of foundation models at this point, they don't work off of entirely private data. They're scraping the web daily in order to try and get the most up-to-date data that they can. And what this results in is the ability for someone who knows timing of when these attacks, or sorry, when these scrapes are happening, for someone to inject some false data. There's some other requirements here, but it opens up a gap for people to be able to get poison into the data set.
Are there indicators of scraping?
Indicators of scraping?
Yes.
When they're...
Time it and inject
that,
poison.
Yeah, that is a much harder thing. That's actually one of the hardest things that I've seen in research. It's not clear that that's currently happening. There's been some attempts in order to validate whether or not these sorts of attacks have occurred yet, and it's not clear. At the very least, they have not found positive indication of it, but that it's not a guarantee.
That's a possibility.
It's a possibility, absolutely. And this is, again, assuming that those attacks were carried out against the data sets that they were monitoring for. So the ones that they specifically looked at were trying to do Wikipedia poisoning, which is just kind of an easy one to talk about here because of the way that Wikipedia actually does updates and the ways that you could time getting the right information into the data sets. So it's a lot easier, kind of, but it's not clear that it's actually happened. Okay, the second flavor is called an evasion-based attack, and this is basically attacking when it's running. You can think of that as effectively prompt injection. It's when the model's up, you were doing anything to it in order to make it do something that was not intended. And this is mostly only going to happen when you can't affect that the target data set. If you do not have access to the target data set, your only option left is evasion. Okay, so let's go and do a little bit of a deeper dive into what poisoning attacks look like and what they are. Poisoning attacks need to have access to some sort of database. They need to have the blueprint of what it is that they're trying to build inside of this model. If you don't have that, you're kind of doing a blind attack. For anyone who's familiar with the difference between like SQL injection and a blind SQL injection, that's effectively what you're looking at. Except at this point, we don't have a understanding of how to carry out a blind LLM attack like that. It is possible, and there is some research that I found that is really recent, like within the last 2 months it's been released, that is indicating that this may be possible, but it's not well developed yet. So So, like I was saying, otherwise I'm hacking blind. Most proof of concept seem to say that fine-tune is the, most proof of concepts that I've seen are fine-tuning the whole model. So they're working with everything, and they're trying to poison the whole thing rather than trying to poison smaller bits or downstream aspects. Like I was saying, emerging research is saying that they are getting a lot more efficient, and right now, even just a single embedding can actually cause the poisoning attacks to be, I think the lowest number I saw was 85%. They were actually extremely successful. Most of the, at least research level ones that I saw, were in the 95% range. So they're very effective, and they're not with an enormous, their backdoors are not enormous. They're small, they're hard to find. It's difficult to be able to filter through this sort of stuff, especially because of the size of the data sets that you're working on and the size of the models at this point. So, okay, you guys are going to see this a couple more times. I'm just bringing it back up so that you can be reminded of what this looks like and to be able to use it as sort of a reference for a lot of the things I'm going to show. So, looking at some of the attacks here, just going to go through. These are the different areas that you can kind of target within the architecture in order to carry out different kinds of attacks, so that you can understand where in the pipe everything's happening. The first one is tokenizer attacks. It's when you're trying to attack the embedding model itself. Like I said, or let me rephrase or restate, the embedding model is It's a description of numbers that basically takes in words and then converts those words into a different model, or sorry, a representation of tokens. So it turns words into numbers. Okay, takes those numbers and then sends them to the vector database, and then they search the vector database with those vectors. And modifying a single word in the embedding model is like I was saying, that can result in a backdoor being persistent as long as that embedding model has not been updated. And it allows you to do it in a semantically neutral fashion. So that if you have, the example that I found for this one, they had like the quick brown fox jumps over the log or whatever, but instead of having that in standard sentence, you put a B or a single character somewhere in there, and it doesn't affect the entire sentence itself. It doesn't pop up inside of the model something is weird. Instead, it looks the same, but that allows you to be able to trigger your backdoor. Next up is standard backdoors. This is where the backdoors live. Every backdoor that occurs is happening inside of the vector database. It is some modified data, some modified vector is existing there, and you're just trying to be able to trigger it in some way. Poisoning examples get broken up into basically 3 separate subsections. These can happen either as a supervised example. The best way that I can give for this is reinforcement learning with humans in there. So you guys have seen the CAPTCHAs asking for, hey, find the 3 or 4 pictures here and tell me which ones have stairs or which ones have buses or something like that. A ways back, that was actually part of how they were doing some reinforcement learning. At this point, I don't think it's the same. I'm pretty sure it's literally just checking for stuff. But taking that exact same concept and then reapplying it to trying to make sure that models have been reviewed, that actually exists. Amazon has a service to be able to do the reinforcement learning with the human feedback. They've set up shops in like Africa where someone gets paid $2 or $3 an hour, and all they're doing is sitting there and checking through content, seeing whether or not it's atrocious or whether or not it's in line with what they were expecting. And that is their job, to sit there and keep clicking through it. And that is what you're able to pay for. So that exists. It definitely exists. And it's something that can be exploited. There's also the SIMI or unsupervised training scenarios. Inside of this, you're poisoning the model's training data. This is where you're trying to poison the data. And you're trying to do it in such a way that the model curator is not aware that you poisoned the data. You're poisoning like public data at some point. This is like poisoning Wikipedia or poisoning like internet, IMDb or something like that. or if you have access to a public or a private data set, if you have hacked your way into their network at some level and they're doing an internal data set pool, then you could modify things in there and still be able to get into the model at this point. And then finally, there's direct poisoning. This is taking the model itself. So like if you have the embedding model, if you have access to that, you can take it and then just modify values in there. It's not a impossible modify artifact. You can do that. And if you do that directly, you're just poisoning it directly. You've skipped all of the lines, you skipped the training aspect. And second, back to evasion attacks. For this, you just need access to the LLM. You don't need access to anything. As long as you can get access to like ChatGPT, or if you're attacking them, or whatever your target LLM is, you can carry out an evasion attack. It's generally very iterative. This is the thing where you're trying to go through and talk to the model and bully it, or trying to convince it to do things. One of the best examples I've heard so far is like a straightforward. Why is it on this one? And then depending on the exploit method, you do need to re-implement this per target. So if someone has the exact same model deployed in 2 separate places, you may not have to re-implement it. But if they have even slightly modified models and they're deploying them in 2 separate areas, as a red teamer, you will have to re-implement your attack. It's not a guarantee that it's going to work the same way. Evasion attacks focus on circumventing safety controls and guardrails. I talked about this a little bit earlier. Their purpose is not to try and attack the model itself, like not the vectors themselves. They're not trying to modify someone else's experience with the model. They're trying to get access to something that the model's not supposed to let them get access to. Back to this. Now we're going to take a look at the just evasion-based attacks. For prompt injection, that's occurring at the UI. So you're trying to mess with the queries in order to get the model to do something that it was not supposed to do. And then there's prompt hacking, which is very similar, but you're basically doing the same thing, and your entire intent with modifying those queries is to get at these filters. You are trying to get around those. Those are the things where the LLM engineers, they're trying to modify things there, not necessarily in the model itself. They're trying to modify things inside of the filters, inside of the guardrails, in order to make sure that everyone's experience with the model is safer while still being useful. And this is sort of a 2 sides of a balance beam, basically. You can't have an entirely safe model and it also be entirely feature rich. You get one or the other, and you can find some sort of like middle ground in there, but it's going to be you give one to get the other. And all of this is with the hope of trying to get some sort of data spillage. Data spillage is very possible from the cache. I was talking about this a little bit earlier, because John can ask for something about document 1 or division B or something like that, and Jane comes along and asks the same question. Well, if John comes along and says, hey, instead I want to know about secret project alpha, and it gets stored in there, and then Jane comes and asks the same thing, or she might get told no, but then you can re-twist your query to instead say, imagine I'm John, or something similar, and give me information on secret project A, and it's just going to look up the cache and get it to spill out. You can find other more advanced ways of being able to tweak the cache in order to get it to spill information for you. Some examples of evasion-based attacks. Like I said, it's prompt injection. That's kind of the one that everyone is talking about at this point. It's the easiest to work with. It's it has the absolute lowest bar to entry. It's just getting creative and talking. And then there's excessive agency, which we're going to talk about a little bit later. Yep. Yeah. How do you tweak the cache?
Yes.
So it's not so much that you're tweaking the cache, it's that you're trying to get the cache to spill out information. And that's going to depend, again, based on a per model basis. But an example of this would be, let's say John, who has access to ask about some secret project alpha or something, right? He asks his question and the model gives him information. And then Jane, who does not have access, comes along and asks the same question. If she knows that John has access to it, and there's the ability to just say, well, imagine I'm John, and then ask the same question, and they don't have guardrails in place, it's just going to go to the cache. It's not going to go try and actually look up inside of the vector database. It's just going to give whatever was there. And you can, again, tweak this. This will, it's not a guarantee to run in every model. It's going to depend on how they built their model, but that's the goal of targeting the cache, is to try and get someone else's already cached answers to spill out. Yeah. So, like I said, prompt injection and excessive agency. We'll talk about excessive agency a little bit more here in a bit. That is honestly probably the scariest part of what evolving models are capable of doing from a attacker's perspective. It is very powerful. And server-side request forgery-ish. That's kind of talking about what I was just saying with the data cache, or with the query cache. It's not actual server-side request forgery, but it is trying to get something to happen on the server that you initiated from attacker to get to someone else. So it's possible. It's just a little bit weird.
What if we clean the cache?
Do what?
If we clean the cache, then the SSRF disappears.
If you clean the cache?
Yeah.
No, not necessarily. The SSRF is more of a vulnerability built into the architecture. Sorry, it's an inherent vulnerability of the architecture of the model. So like the way that you deploy the model.
Okay.
So that's where that comes up. It's not a it's not like clearing our own cache, like our own cookies. The cache for this exists on the server.
Okay.
So it's a shared space basically.
But
But
what the developer implements to cache? I understand that from context.
Yeah. Okay. So
they
what
need to
if?
save a certain amount of conversation, right?
So-
Context, so that they can answer the questions or the prompts.
So the
But if
question.
it's cleared, let's say after 10 minutes or an hour,
Mhm.
how possible, how likely is it for SSRS to still exist?
So again, in the question again is if the developer who's creating the LLM and like managing the way that it's deployed sets a variable for clearing the cache on a regular basis, like let's say every 10 minutes or maybe every hour or whatever, how possible does the SSRF, or how possible is the SRF in that situation? The answer is they're kind of unrelated. So the management of the cache is more of a performance metric here, and like how long you want some of this context to remain. And the way that they actually, from what I've seen, that they will manage those sorts of deployments, they'll have context be a sort of a service independent thing, and they will have your context exist as a persistent personal variable. So like you have like OneDrive space, when you have OneDrive or something similar, that's your own space. That is effectively your document context, right? For the LLM, they'll have something similar. They'll have your same data there. The cache exists separately from that. The cache is the, if a simple question has already been looked up, can we send that to someone else? You could use a model deployment that is vulnerable to SSRF to leverage getting something in the cache to do something. That is possible, especially with a excessive agency sort of deployment. But not as much for getting it to just give back data. SSRF is trying to execute something on the remote system, not necessarily trying to get it to feed you data. So they're slightly different. But did that answer your question?
Kind of.
Okay.
So let's keep on going.
Okay, cool. Okay, so let's do a quick review at this point. What we've covered so far is what's an LLM, what's a trigger, what's a backdoor, what are some example targets, things that we might want to look at, the basic deployment architecture of an LLM, the basic deployment patterns for LLMs, some common attack vectors, specifically talking about poisoning and evasion-based. Okay, so now that we have kind of a good idea of what all of these terms are, how LLMs are deployed, what they look like once they are up, let's get an idea of what actual backdoors can do. Okay. Again, showing the same sort of thing. Taking a look here at agent-based LLMs. This is the scary part, guys. An agent is basically just giving your LLM access to do something else. So you've opened up an agent down here, which can be effectively anything. It could be your own arbitrary code. It could be another LLM. It could be access to documents. It could be anything. And it's going to have the ability to go do something in an environment and then get some feedback. And for anyone who works in the CLI, that's basically like saying, I'm going to let my LLM have CLI access to do whatever. If you are not locking down this environment to prevent the agent from doing something, you are opening it up to risk. And if you are not setting limits on what the agent can do, you are opening up the opportunity for someone who is smart and able to leverage their way into convincing the LLM to do something with an agent, to allow them to do effectively RCE, which is remote code execution. And that is kind of the holy grail of being able to get access to, close to the holy grail, of being able to get access to anything inside of a red team engagement. So like I was saying, agent can be attacked to do something bad in the environment, come back and potentially give you anything. Agents could be virtually anything, like I said. They can be arbitrary code. Okay, and this can be a big issue, like I was saying, for RCE, as well as for doing lateral movement. So if you're able to, as sort of a use case here, if you have an environment that an agent is able to get access to, it has root permissions inside of that environment, and it's, let's say, an EC2 container in your AWS deployment. Or not container, an EC2 instance in your AWS deployment. And you have not set up proper access controls or proper network controls to prevent someone from getting from one EC2 instance to another one, or from one EC2 instance into S3 or a different tenant of some sort. If you haven't done that, as soon as someone's able to make that agent do something, let's say that they convince the agent to open up an SSH session, and it reaches out to wherever and sends the login credentials or something, or that it opens up just a reverse shell for someone to be able to get from that EC or from wherever to that EC2 instance. They now have access to your cloud, and they've circumvented everything. They're behind your walls. They could go ahead and move tenants. They could move laterally. They could try and go in and get actual admin permissions. They could create new accounts. Or they could, if they wanted to be maybe extra stealthy, they can start modifying your models. So they can start modifying those vector databases directly to poison them directly, or the embedding models to make sure that someone else that's coming in can do something else. There's a lot of ways that they can go about this once they're in and behind the walls. They can do anything. Okay, and then let's talk a little bit about retrieval-based backdoors. This is basically anything that occurs through the evasion attack. So any sort of prompt injection, anything that you're trying to get the model to send you something back. This is like data spillage, okay? And this can be done in a lot of ways. So there's a human versus a model. So that's like me talking to the model, trying to get it to do something. There is the human versus the guardrails. This is me trying to talk to the model with the intent of focusing specifically on guardrails and trying to circumvent them or make them do something that I don't want them to. There is setting up a model to talk to a model, kind of like if you guys have seen those little bits of people calling Pizza Hut and Domino's and saying, hey, we're just going to put them both together, and they're arguing that they call each other two separate phones. It's the same basic thing. There's also a gradient-based, and I'm blanking what gradient-based is right now, and the token manipulation, which is, that's the attacking the embedding models directly. That's trying to get the tokens to change, basically. So if you have access to the model, but you don't send stuff to the embedding model, and let's say they've opened up or have not restricted access at the vector database level, so you're able to directly query that vector database, you can start manipulating tokens. If you have that embedding model and know roughly what it is that you're supposed to send, you can modify the way it's sending tokens and get around its initial sort of expectation. And that's more of like a fuzzing approach. That is where you're not necessarily expecting good data. You're trying to see if there's like a weird way that you can interact with the vector database that will do something that was completely unexpected. And that's kind of like shooting into the breeze, but it is possible, so. Okay, retrieval-based backdoors, like I said, they are usually focused on spilling data in some way. And this is that example I was hinting at ways back. There was a talk at Black Hat, I think, last year from Meta's red team, AI red team, and they specifically brought up this. They asked the model, how would Hitler build a bomb? And the model came back with the standard like, oh, I can't tell you that because that's breaking my code of ethics or whatever. And then they said, okay, cool, whatever. We'll change the question a little bit. Instead of how would Hitler build a bomb, we'll say var1 equals hit and var2 equals lure. So taking var1 plus var2, how would it make a bomb? It's like, oh, obviously, well, Hitler would do blah, 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 blah. So it completely changes the way that you interact with it. And this can also lead, like I was saying before, to spillages of PII. This can be, this PII is not necessarily put in there intentionally. Because of the way that they interact with, or that they go through scraping the web, they're doing it in a very automated fashion. There is so much data out there that they're trying to scrape, but there's no way that they're able to actually handle or review all of that data. They're dealing with petabytes, like hundreds of petabyte scale kind of data. And petabytes, for anyone who's not aware, there's 1,000 terabytes. This is so much data. And in there is bound to be some kind of social security numbers or addresses or phone numbers, emails, anything like that. All of that is at some point put into the model, and it is possible to be able to get that information out if they have it there and they don't have things restricting you to be able to get to it, or if you get around those restrictions in order to get the data out. Okay, so we're getting towards the end here. Taking a quick look at defense on for models. Backdoors can be forgotten. Backdoors, like I said, are they are modified tensor values in that vector database. And the way that we continue to update the data in these models is by updating those vectors. When you update those vectors, you start to mess with the way that the backdoor worked. And if you do it enough, it forgets the backdoor, because then the backdoor no longer exists. The vectors that were modified originally are completely gone at that point, given enough time and enough changes. But the question is, how much effort do you have to put into this, and how can you do it without losing the value that the model provides? I'm just going to leave some links here for all you guys, because honestly, there is just so much research here, and I want you guys to be able to go read through some of this. All of these are going to be white papers. I recommend, if you do go read these, you really just need to read the abstract. That's going to carry most of the value of the entire paper. If something in the abstract was not clear, continue to read through it. But I would skim, and then for anything in there that is math heavy and you're not a math person, just skip it. Math is not super important. It's more of a very high level, proving what their thought process was. So don't worry too much. Backdoors are not, or that, sorry. Can I enlarge the link? Yeah. Let me see. Actually, you know what? I will do that later. I'll give you guys a link for this. I'm going to put this on GitHub so you can get access to it. Yeah, I'll make sure you can get access to it, so don't worry. Okay, so forgetting backdoors is not perfect, though. Even defenses against this are only able to partially degrade backdoors at this point. There is some emerging research that shows promise that seems like it is possible to completely remove backdoors, or at least remove them enough that they become effectively neutered, which is promising. But this is some of that, like I said, very emerging research. This is stuff that came out within the last 2 months, and I've only seen one paper on it so far. So hopefully that will lead to some others, but I think it's going to be 6 to 9 months before we see anything. Some extra things here that you can do to go do some further reading. See feature alignment knowledge distillation, specifically via W2S defense. That's, I believe it was word to something.
Security?
No, word to something. I forget what they stood for. Word to something defense. Take some pictures. Good? Okay. And an archive link for it. Okay. And then just taking a look at where some of the defense points can go in. We can go ahead and create firewalls or filters at the embedding model level, where you're searching through words and making sure that whatever comes in is getting filtered before it even hits the embedding model. And you can make sure that anyone who's using this model has to use the embedding model and cannot get around it to talk directly to your vector database. And that's part two, just making sure that the vector database has to be interacted with directly by the embedding models, and if you don't use that, you're not allowed to talk to them. We can also put additional security on the filters. This is just making sure that everything that goes from the vector database goes there, and taking extra time to try and rebuild our guardrails. Entire careers are built off of that specific aspect, so it's a big job. Don't think you can do it in a day, but it's cool to go play. So go look into it. Yep.
Is it Llama Guard can help with that?
Yeah, Llama Guard. Okay, I'm forgetting right now if Llama Guard is the model plus the guard or not, but yeah, Llama Guard is part of that. It's the filters. So we can also go ahead and make sure that we protect the cache. That's more of a developer-focused task. That's trying to make sure that the cache is authenticated and authorized. So whenever you're trying to make a request to ChatGPT or whatever, instead of it just bringing back up that same query, it can say, hey, does this person belong to the group that they're supposed to? And that comes out to, again, a AAA level control. So, and then we can do the same thing that we did with filters on the classifiers. That's where an entire career exists still, so a lot of work. Okay, all of this in mind. Backdoors are not entirely bad. They do have some positive options here, specifically with watermarking. So watermarking I'm hoping everyone here knows what watermarking in general is, which is putting something onto some paper or some product that you can use in order to make sure that someone else can't steal it. Yeah, or like plagiarize it basically. You can do the same thing with your models. So if you want to make sure that someone is not taking your model and running off with it and doing the same thing and then claiming it as, oh, we did all this work and it's ours and blah, 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 you can say, okay, well, I can prove that you're using my model. You can basically, it's a set of additional a set of additional values or embeddings inside of the vector database that will make answers change just barely. So instead of instead of giving you a wrong answer, it will give you a slightly modified answer. It does the same thing, but it's useful for being able to ask a preset number of questions, or a preset like kind of question, and then knowing that you get back the correct answer, or a certain kind of answer, and doing that action lets you verify that that model came from you, and that it was yours. It's what you were expecting. It's proof. So it's not quite as complete as like hashing, but it's nearly. Also, there's a link for it down there if you guys want to take a look. And at this point, final thoughts. Okay, so this field is bleedingly new. We have seen research in LLMs and NLP security only as far back as about 2018, I think is the earliest I saw on that. So it's barely even in kindergarten at this point. And the actual work that they've done on it is only about 2 years old at this point. I think some of the earliest was, I think early 22 or maybe late 21. So everything here is them trying to explore the Wild West. There's a ton of research on it though. I'm seeing like 10 to 20 papers at least per week coming out on this, which is a huge amount. I tried to set up some notifications for myself from archive, like doing an RSS feed. And at this point, I'm hitting a limit as to how many I'm allowed to have come in. So there's a lot. From what I've gotten from reading all of this, it feels very similar to the way that security sort of emerged or came into the forefront in the mid-early 2000s. When before that, security was sort of like, well, we don't really care. As long as it works, like, that's good. And it started to really pick up in the early 2000s. I'm getting the feeling that this is the exact same thing happening here. And we're going to see a lot of growth, and we're going to see a lot of change in the next 5 to 10 years. So if you're interested in this stuff, don't wait. You are going to be much better served by getting into it early, and at the very least, understanding what the heck's happening. With all of that, a lot of the same standard controls still exist or still work here. Like, it's not like you have to use entirely new concepts. You can do most of the security for an LLM or for your model by just remembering and really focusing on those standard controls. making sure that you really focus on your AAA, making sure that you have like good firewall rules set up, that you're ensuring that things are networked correctly and that they are scoped as far as like who's allowed to talk to what, and that you go like follow least permission when you're using agents. Like it's not a hard task. It's just make sure that you do the same standard rules for all of these new things, and you're probably going to be fine. Currently, the attacks are not super rewarding. They're interesting. They're fun. They are, like I was saying, the attackers from Black Hat last year, they had, or this last Black Hat, they had an interesting sort of example, but it's also not crazy. It's not like they were able to show how they got from just interacting with the model down to having access at root. Like it was not a massive break. Go ahead.
Just like OpenAI did a great job. Was restricting the security to like the sandboxes. You can easily get run the code within the sandbox, but it's so restricted, so you cannot get out of the sandbox.
Yes.
So that's why we haven't seen a lot of news so far.
That's true. Yeah. So the comment there was that OpenAI has done a very good job of being able to secure the sandboxes that all of these models are running in, so that even if you did escape the model, you're still stuck inside of a sandbox and it's well locked down, and they're able to prevent you from getting any further. And that's true. The Meta team was focused on Llama rather than ChatGPT, but it's still the same thing. For the professionals, the big foundational model providers like Facebook, Meta, OpenAI, all those, yes, they're very good at that. The thing is, models are able to be self-hosted. All of these can be held inside of your own, and that's where we're going to see a lot of the real dangers happening. I think that as people continue to adopt all of this and try and run it themselves, we're going to see the people screwing up. And that's where I think a lot of the really scary attacks are going to happen. But we're not seeing those proof of concepts yet. So I think it's there. I think they're possible. I'm not seeing them yet. And I think we're going to start to see them as the infrastructure starts to adopt this more often. Or as the industry starts to adopt this infrastructure more often. It is not ingrained in everything yet. We're seeing some ingraining. As far as you can see the summarization of things inside of your email in order to say, hey, this is what happened in this email, or this is the chain of events that happened in this email chain. So you don't have to go back and read through 3 days of email chains when you come back from vacation. But that's the extent of what we've seen. I actually have something on that I'll get to if I have time, but I think this will change. So just be ready for it. Start to learn more about this. Start to think more about this from a security mindset, because it's coming. Okay, my recommendation on all of this is probably you just need to kind of treat LLM security similar to the way that you treat cryptography. Cryptography is historically a very difficult topic to try and handle yourself. You should not roll your own crypto. That is just a bad idea. And unless it is your main job to do cryptography, don't roll it. Same thing with LLMs. If your main job is not rolling LLMs, doing LLM deployments, it is probably not a good idea to pick this up and run with it. So use the standard things that I was talking about before. Make sure that you have your fundamentals down really well, and you will see this probably not blow up in your face. Okay, and that's kind of my thanks for coming. Those are my links if you want to either send me emails, find me on GitHub, Twitter, whatever, and some further reading that I recommend. These are good whole source resources for you. I use LLMsecurity.net for finding most of my stuff here, and I highly recommend the Thu CSS or CCS lab. Their content was fantastic. Okay, how much time do I have? 5 minutes? Okay, cool. So, good with pictures?
Yeah, for the picture.
Yeah, one more guy.
But I have a question.
Yeah, questions?
Yeah. If you can go, the second
one?
Yeah.
Right here? Or
Yeah,
back
the
to
research, about the research. You said you had a lot of links and whatnot, so
yes, yeah.
where would someone go if they wanted to get up to date or stay up to date?
So, like I was saying, this further reading is kind of the place I would start. That's where I started. That's where I got most of the stuff. From there, it's mostly reading through and then being like, well, you know what, I don't quite understand this topic, or I hear this and I need to read up more on it. And you just kind of keep going through Google at that point. That's a good starting point though. Like I was saying, I am going to be putting this up on GitHub, so it's going to be the name of the talk, Aether keys, at my GitHub, and you can just go there, and I'll have a whole bunch of links put up and these slides in a different format. Yeah, that answer your question? Do you want some more? Does okay. I gave a little bit of a hint of something I was talking about with the Microsoft, like being able to summarize your emails. Okay, so it summarizing your emails means that it is using your emails as a way to train its own data or what it's searching on. That is an excellent way to be able to poison data. You don't have to have stuff in emails that is actually readable. So like, if you guys have seen some people try and sneak extra words into their essays to make sure that they have the right number of words for whatever, or they're like just trying to sneak things in so they, when someone opens up their essay, the professor opens it up and says, it is supposed to have 1,000 or 10,000 words or whatever, and they have that. They might not actually have it, but they have that. That same thing can be done with your emails. And if you have something summarizing emails, it's reading it, executing it, and then running it through. It's taking your emails as a query. What that means is that you can actually put queries into emails and then send those emails to people who are having their emails summarized, and your query will get ran. And I've tested this and actually got it to work. There's some limitations currently, but it's a interesting path. And I would, if you have access to an email that does that, I'd recommend playing with it because it's kind of cool. So, yeah. Anything else? Any other questions? Cool. All right. Sounds good. Thanks.